So I wanted to give a little more explanation about section 10.4 from the textbook, which is looking at comparing the proportions of two separate or independent samples. So we'll look at both interval estimation of the difference between the proportions, so the little p's here for proportions from sample 1, and we're subtracting proportion 2. That's the proportion from the second sample, which is independent of the first sample. Then we'll look at hypothesis test also. So the sampling distribution of the p bar 1 minus p bar 2 is just the, all we're saying here is that it's unbiased, right? So the expected value of the sample proportions is equal to the true difference in proportions, which makes it unbiased. And then the standard deviation or standard error of the sampling distribution is this guy here. It's the proportion minus its from the whole divided by its sample size. So n1 is the sample size that we're taking from population 1. And then do the same thing over here, take the square root of the thing. So if the sample sizes are large enough, if n1 and n2 are large enough, the sampling distribution can be approximated by a normal probability distribution. So that unbiased part back there before, the expected value equaling itself, means that will be the mean of the normal distribution, and then the standard deviation or standard error is how much the normal distribution will be dispersed, so how fat the tails are. So the sampling sizes are sufficiently large if all 4 of these conditions are met. So all 4 have to be met. If one of them is not met, we cannot assume a normal distribution, so we cannot use this test. So it's basically the sample size from population 1, sample 1, multiplied times the hypothesized proportion from 1, and it has to be bigger than 5. And we subtract it from the proportion from 1 here. So remember, the proportions are a number between 0 and 1. That's going to be greater than 5. Same thing for the second sample that we're looking at. So everything in the textbook that you do for homework and stuff that should meet that condition, but it wouldn't be a bad idea to check just to make sure. So again, the unbiased part gives us this, that the middle is right here, and then we're approximating about a normal distribution, and the dispersion, how fat the tails are, is given by this guy up here. So to get an interval estimate for the difference between two proportions, this is true for all interval estimates. We take a point estimate and we add and subtract the margin of error. So the point estimate is p bar 1 minus p bar 2. So this is the point estimate. All point estimates are wrong, so that's why we're doing an interval estimate. So we take this point estimate and we add to it the margin of error. We're doing z alpha divided by 2 because we're adding and subtracting. We want a two-tailed here. The interval by definition is two-tailed. And we're multiplying times the standard error. So we got point estimate plus or minus the margin of error. So the z value we can look up in the table. If we're using 0.05 for alpha, then our standard z value is 1.96. It's slightly less than that, but that's what we generally use and what's usually in the table. So let's look at an example for interval estimation. So we have a company that does marketing research. They're trying to evaluate the effectiveness of a client's new advertising campaign. So ideally, marketing people will tell you that their advertising campaign will bring in this much more revenue or this many more exposures, things like that. So before the new campaign began, a telephone survey of 150 households in the test market area showed 60 households were aware of the client's product. So it'd be nice to have more information about what that word aware means. They had heard of the product name, they had used it, so what, got some fuzziness going on, but that's okay. So 60 out of the 150 were aware before they started advertising. They advertised with this new campaign with TV and newspaper ads running for 3 weeks. And so we'd like to know that how many people were aware after. So after those 3 weeks of advertising, they called 250 households, and 120 of them said that they were aware of the client's product. So notice first off that our sample sizes for before and after are different. That's perfectly fine. So N1 and N2 do not have to be the same. So now the question becomes, does the data support the position that the advertising campaign has provided an increased awareness of the client's product? So on the surface, it looks like it has. So the question then becomes, is it statistically significantly better? Did it actually get more based on that, right? So we're going to do that first with an interval estimate. So we're going to define some things. We have to define what is the population of households before and after. Right, so population 1 and population 2. So I'm going to define the proportion of population households aware of the product after the new campaign as P1, the first population. And the before is going to be the after, or the P1 is going to be after the campaign has been done. P2 is going to be before the campaign is done. So then the sample proportion after is P bar 1. Sample proportion of households aware of the product before the new campaign is P bar 2. Now why am I doing after as 1 and before as 2? It's because I know, looking at the numbers that were given to me, that the proportion after the new campaign is bigger than the proportion before the new campaign started off. And so when I subtract P2 from P1, P bar 2 from P bar 1, I get a positive number. I like positive numbers instead of negative numbers. That's really the only reason I did it. Alright, so we know that 120 households were aware after the campaign out of the 250 that we called, so that's 0.48. And then before it was 60 out of 150. 0.4, so we get a point estimate of 0.08, so 8%. We've raised the awareness by 8%. So the marketing consulting group that you got to do the campaign will say, look how good we did. So now the question is it statistically significantly better? Right? Let's do the following. To do some of these numbers, I'm going to move over to Excel for a second. So before we had 60 out of 150, and after we had 120 out of 250. So unfortunately there's not a, this is going to be P1. Let's do population 1. Unfortunately, there's not a nice add-in from the data analysis toolpack to do this for us, so we have to do everything by hand. So that's why I've got this over here. It'll help us in a minute. So to get the proportion, we take the aware out of the total. All right, so before it was 40%, after 48%. So the point estimate, which is this part right here, P bar 1 minus P bar 2, is 1 minus 2, so 0.08, right, which is what we got. So now we want to calculate the interval estimate. So now we need to find the margin of error. So this part here is the point estimate. And now we want to calculate the margin of error. which is the Z and all that other stuff. Right? So let's do this in pieces, perhaps. Let's do the thing under the square root first. So I need, the first part here is p bar 1 times the quantity 1 minus p bar divided by its sample size. So p bar 1 is the 0.48 times 1 minus 0.48, which is 0.52, but I purposely am using the reference instead. Alright, so that needs to be in parentheses because I will need to subtract it from 1 first. And then divide by the sample size, which is 250. And so I get a small number. If I actually make this bigger, right, it's a small number. So then we need to do the same thing over here. So if I do that, see if it does it right. Yep, 0.4, 1 minus 0.4 is a 0.6 divided by 150. Alright, and again, that's, it doesn't change, that's nice. So now we need to add those two together. So I'm going to do that down here. I'll use the sum function. You could just do addition if you want, but because they're contiguous, I'm going to do that. And then we need to take the square root of it. So again, I'm doing this in steps. I could embed all these formulas, but just so it's clear, I'm doing this. All right, so I get 0.0509745. All right, which is the standard error, right? Is what we had to come up with before. So let me do this, and now we need to find the Z value. So in Excel, it's nice to use the functions that are built in for us. There's a function called norm.s.inverse, and you need to give it a probability. So here you give it the alpha divided by 2 is 0.025. So let's try that. I know that it's wrong, but let's try it anyway. It'll say a Z value of negative 1.95999. Okay, we know it's supposed to be 1.96, not negative. So that means I need to put in instead of the 0.025, I need to put in the 0.975, and that gives me about the 1.96. So it's like almost 1.96, right? So then the margin of error is the Z value times the standard error, the 0.051 that we came up with. So my margin of error is 0.09991. So then my interval estimate, the low end, will be the point estimate minus the margin of error. And the high end will be the point estimate plus the margin of error. So low end of interval estimate and high end of interval estimate. So what does that tell me? That tells me that because 0 is contained within that interval estimate, that the campaign had no statistically significant difference in making households aware of the product. So the average, we spent money that we shouldn't have spent money on, is basically what that's saying. All right, so look how wide that is. The margin of error is bigger than the point estimate, right? So when it's bigger than the point estimate, we're going to get 0 in there. It means we can't do anything about it. So at the alpha equals 0.05 level, 5%, we cannot say that the new advertising campaign was effective. So let's go back to the slides and see what happens next. So we did this, right? And so we came up with 1.96 like we did there. So here on the slides I rounded it slightly to that and rounded this slightly. So the interval estimate here, I didn't put it in the high and low ends, but if you subtract the 10 from the 8, it's negative 0.02. Or if you add it, ours was a little different because I didn't round it in Excel. Hence, the 95% confidence interval for the difference is before and after awareness. The product is negative 0.02 to 0.18. So again, because 0 is included in that interval, that means that the advertising campaign was not statistically significant, did not help us improve our awareness of the product. So now let's move on to hypothesis testing. So again, we are looking at two different proportions, and we can have a left-tailed, a right-tailed, or a two-tailed. And we're going to focus on no difference between the two populations, which means P1 equals P2, which means the right-hand side is going to always be 0 for the stuff that we're focusing on. Now, there's nothing stopping us from making it not equal to 0, right? If we think one is so much bigger than the other one, we could test for that. Again, the burden of proof lies with the alternative hypothesis, the H sub A. So we need to look at an example. So the standard error, again, so when we're assuming P1 equals P2, we just use P to represent both, so we get a slightly different standard error. It makes computation slightly easier. And then we pull the estimator of P to just be P bar, right? All that is a weighted average of the two P bars. And then the test statistic is a z-value, because we're assuming again that it meets all 4 criteria that we looked at before, the n1 times the p1, etc., greater than or equal to 5. So the test statistic is a z-value. We'll take the sample proportion from 1 minus sample proportion from 2, and we'll divide by this pooled estimator times 1 minus p. So this is going to be different than this guy on top. This is basically the standard error down here that we're looking at, that we're dividing by this guy up front. Right. So we'll go back to the same example, but this time we'll do a hypothesis test instead. We'll walk through the 5 different steps that the book walks you through. Can we conclude using alpha equals 0.05 that the proportion of households aware of the client's product increased after the new advertising campaign? So when we did the interval estimate, we were doing a two-tailed, which said, did it change? It did not change because 0 was in the interval estimate. Here we're asking a different question. We're asking, did the number of households aware increase? So here we're only interested in a one-tailed test. So then the question becomes, which tail are we looking at? Well, again, I like to draw pictures to do this. I'm not going to draw it right now, but remembering that the burden of proof lies with the alternative hypothesis. P1 again was the after the campaign, so P1 minus P2 is greater than or equal to 0. How did we get this? How do we know that the alternative was this? Well, we said P1, I'm trying to test whether P1 is bigger than P2. Well, if I add P2 to both sides of this bottom equation here, I get P1 greater than P2. That's exactly what I'm looking for. And I put it in the alternative because I have to be able to reject the null to believe in the alternative. Right? And then the null then becomes P1 minus P2 less than or equal to 0. Right? So again, we defined P1 and P2 as we had done before. So that's step 1. Step 2 is specify the level of significance that was given to us as 0.05. Step number 3, compute the value of the test statistic, which was the z-value. Right? So first we have to calculate the pooled estimator of P bar, which is the weighted average. You take the 250 times its proportion plus the 150 times 0.4. Right, divide by the total sample size, so you get 180 over 400, which is 0.45. Notice it's not 0.44, which you would get if you did the 0.48 plus the 0.40 and divided by 2. That's just a regular average. This is a weighted average. We're weighting it by the sample sizes, right? So this gets more weight because it's bigger sample size. Then we calculate the standard error, all right, which was on that we had the formula back a slide or two, and then from there we can find the z-value, which is the 0.48. That's the sample proportion after, minus 0.4, the sample proportion before, minus 0. The 0 is the difference that we're interested in. So it's whatever follows on the right hand side of this. So for I think most of the homework problems and all the examples use 0 on the right hand side. You could easily change that to 10. All right, so it increased it by at least 10 percentage points. Right. Here we're just interested if it increased it at all. All right, so we get 0.08 on top, and we divide by 0.05, and we get a z-value of 1.56. We look that up in the z-table, and we determine whether or not to find the p-value, and then we determine whether or not to reject or not reject the null hypothesis. So maybe let's go and do some of this in Excel to make sure that our numbers are doing the right thing. All right. So hypothesis test. I think I put some over here. Okay, so let me do this. I'm actually going to do this. Control C. I'm going to be copy and pasting a little bit here. All right, so P bar. Let's calculate P bar, which is the pooled estimator. So it'll be N1, which is 250, times P bar 1, plus N2, which is the 150, times P bar 2. All right, and I need to put parentheses around those guys. And then divide by, open parentheses, 250 plus 150, close parentheses, and we get 0.45, which is what we had come up with before, P bar. Right. All right. So then for Z, we're going to take P bar 1, 0.48, minus 0.4, and then divide by the standard error. So I still need to divide down here. So let's calculate the standard error. All right, which is the denominator of the z-value there. So let's do square root of P bar 1, no, just P bar, which is this guy, P bar times open parentheses 1 minus P bar times open parentheses 1 divided by 250 plus 1 divided by 150, close parentheses, and we get 0.5138. I think on the slides I'd rounded it to 0.0514, which is fine. So then Z, I need to divide by what I just came up with, this guy. So I get a Z value of 1.557. On the slides we had come up with 1.56, so I must have rounded it up. Plus this right here was rounded up as well. Right. So this is the test statistic. Right, so that's step 3. So let's go back and go to step 4. Compute the p-value. For z equals 1.56, the p-value is 0.0594. And in step 5, determine whether to reject the null hypothesis. Because the p-value is greater than alpha, we cannot reject. So we cannot conclude the proportion of households where the client's product increased after the new campaign. So we get a similar result that we had before, but this time it's a one-tailed test. So it did not increase the awareness. So again, hopefully you didn't pay the consultant. So how do I get that p-value in Excel? So I want the, let me come down here maybe, p-value. So there's another formula in here called norm s dist, which takes the z-value, which we just did, all right, and a second parameter called cumulative. We want true, which means give me everything up to it, because it's the probability distribution, the cumulative distribution function, not the density function. And notice that that will take me everything from negative infinity up to z equals 1.557. That's fine, but what I really am interested in is the right-hand side of that picture of the normal distribution, had I drawn the picture. So what I need to do is simply take 1 minus that. And I get a p-value of 0.05974. Right? Which is actually bigger than what is on the slides, simply because of the rounding. So again, then what we can do is, let's see, let's put in alpha here, why not? 0.05, alright. And then if this is bigger than this, do not reject, else reject. So do not reject the null, right? So that finishes up looking at proportions for 2 independent samples, assuming we can use, assuming the sample sizes are large enough and all that fun stuff. We looked at interval estimates, which is two-tailed, right? It's a point estimate plus or minus the margin of error. And we looked at a hypothesis test using a one-tailed test, where we're interested in whether or not it increased awareness. So hopefully that helps you with some more understanding of section 10.4 from the textbook.